The core architectural bottleneck of the Bitcoin network is its reliance on a sequential, one-dimensional linked list of cryptographic blocks. It forces the system to store a continuously growing history, scaling linearly with time. However, in topological computation, temporal processes can be simulated using memory proportional to the square root of time. By treating states geometrically, infinite branching is bounded within finite memory. Current data reduction methods try to solve state bloat by discarding data. Techniques like simplified payment verification, a method allowing nodes to verify specific transactions without downloading the entire blockchain, drop bulk data entirely. This approach destroys the dynamic, relational structure of the network's history. To retain that structural data without the storage penalty, we must replace the linear sequence of hashes with a multi-dimensional architecture. We do this by applying topological data analysis. Topological data analysis is a mathematical framework that extracts meaningful geometric shapes and patterns from complex, high-dimensional datasets. By folding historical data onto a closed topological manifold, the network contains its infinite temporal history within a bounded physical memory space. It maintains absolute cryptographic security while containing the expansion of the system state. To compress the ledger, we first translate the linear, one-dimensional block states into a hypercomplex algebra known as Quaternions. Quaternions are a four-dimensional number system specifically designed to calculate continuous spatial rotations. This animated diagram demonstrates how the linear blockchain is ingested. Instead of a flat timeline, the states evolve as a time-ordered sequence of discrete coordinates distributed across the surface of a three-dimensional sphere. If we isolate two adjacent states on this sphere, we can draw an arc between them representing the transformation operator. We find the next state using Quaternionic delta encoding, a method calculating the relative rotational difference. Because Quaternionian multiplication inherently represents rotation in 4D space, applying this delta ensures the new state strictly adheres to the curvature of the manifold. It mathematically eliminates the floating point state drift of Euclidean matrices. Quaternions are non-commutative. In this algebra, multiplying variable a by variable b produces a completely different geometric result than multiplying b by a. The order of operations dictates the final spatial coordinate. This non-commutative property acts as an order-dependent cryptographic trapdoor. It mathematically mirrors the chronological security of a standard hash function, but maps it into multidimensional space. A standard blockchain treats all data as acyclic. But in reality, financial networks exhibit highly cyclic, recurring behaviors, like daily volume spikes and consolidation loops. To exploit these recurring behaviors, we apply our topological data analysis to the point cloud of Quaternions. This animation displays a Viatori's Rips filtration. A Viatori's Rips filtration is an algorithmic process that grows expanding spheres around individual data points until they overlap, connecting them into structural networks to map the geometry of a dataset. As the arbitrary noise fades, it reveals distinct topological rings within the financial data. The output of this filtration is a barcode diagram, where the exact length of each horizontal bar corresponds to the structural stability. From this diagram, we select a value of k equals 2. We are mathematically isolating the two longest bars, which represent the two most dominant recurring structural patterns in the network's history. By isolating these specific loops, we separate the structural cycles of the financial system from arbitrary transactional noise. We now have the fundamental frequencies of the network. This diagram illustrates how we construct the bounds of the new consensus layer. We take those two isolated frequencies and project them to form the principal axes of a two-torus, a closed donut-shaped mathematical surface. To optimize this structure, the outer and inner radii of the toroid are strictly defined by the Golden ratio. This creates what is mathematically known as a Golden-Clifford toroid. The discrete behavioral loops are parameterized into continuous circular coordinates, ranging from 0 to 2 pi. By combining both rotational loops using Quaternion multiplication, the system calculates the exact coordinate value for any point. As new transactions enter the system, the chronological data stream wraps around the toroid, laying down paths side by side without ever intersecting its own trail. The Cust-Golden ratio dictating the two rotational frequencies is perfectly irrational. The data trajectory mathematically cannot intersect itself. This irrational geometric wrapping provides an ergodic covering of the state space. An ergodic covering means the trajectory will eventually visit every distinct part of the surface evenly. An infinite transaction history is captured on a strictly bounded surface. This animation shows the continuous surface segmenting back into a finite, discrete grid for actual node storage. The coordinate at each point is packaged into a dense instruction packet containing a compressed geometric field. The full precision coordinate is compressed into that space using E4M3FP8 quantization. This low-precision floating point format uses 4 bits for the exponent and 3 bits for the mantissa to achieve high data density while preserving geometry. Beside the geometry, the packet includes contextual fields. The structural form ID field acts as a direct pointer to pre-compiled computational kernels on the hardware. This architecture replaces massive linear transaction vectors with dense dynamic computational instructions that inherently encode their own topological history. Because the packet is structurally self-aware, validating nodes can instantly identify if a geometric path computation is redundant before executing it. This cache awareness reduces the required processing power across the network. This generated lattice illustrates a critical vulnerability in continuous spatial computing: fractional floating point drift. Floating point drift is the accumulation of microscopic rounding errors in computer math that, over millions of continuous iterations, causes ledgers to fall out of consensus. To prevent the network from fracturing, the Quaternionic Upgrade utilizes an automated defense mechanism called the spinor cyclic constraint. This spatial computation counter relies on the Dirac belt truck, where quantum spin 1/2 objects require exactly a 720-degree spatial rotation to return to their unentangled state. Enforcing this modulo 720 clock ensures iteration 720 naturally yields the identity matrix. This cyclic return acts as an automated zeroing function. It purges fractional drift and achieves integer synchronization among all validating nodes. Mapping the protocol into a self-stabilizing quaternionic matrix constrains the network's state memory to a static phase portrait. This configuration allows distributed ledgers to leverage high-throughput tensor hardware and AI-on-chip architectures by replacing transactional vectors with context-aware instructions.